So Simona probably answered all the questions. Yes, do you have any questions? No, you didn't? Didn't answer any questions? Okay, well, I'll answer all the questions now. So now it's the most exciting part. So listen carefully. So I just remind you everything that we've been doing, just schematically, so that you see the logic. So there was the following, right? So we had a group which we just chose to be the multiplicative group. I'll work over complex numbers, and nice, smooth, probably projective variety X acted upon by the group. And so we did the following. We defined an object like this, X TL, which was just X cross CL minus the origin, and all this divided by groups. So we take the orbits of the torus action, and then we defined the equivariant Chow groups of X as the limit, as L goes to infinity, of the Chow group of, it's just the ordinary Chow group of this XTL. And in every particular case, it was clear what I mean by this. I didn't define this formally. But an even more undefined but formally relatively clear is that we also sometimes, I use this notation, I might, so I warn you, use this notation that there is this sequence of spaces goes to this limit space in some category, which is not our category because it's not going to be a projective variety. Okay, but this thing will be well defined and we calculated in a few cases. So the examples we had were, say if X was a point, then we saw that XLT is just equal to L minus one dimensional projective space, and naturally then this AT of X is just okay. So the first thing this is sort of our basic thing, and then we introduced bundles, and we introduced equivariant bundles. And so here I wanted to reflect on, I mentioned that there is some sign problem, so I want to explain that a little bit, this sign issue, okay? So the sign issue is the following. Let's just, so first of all, clearly, whenever I have just a second. Yeah, well, let's just do this example, or one can do it more generally. So one remark I would like to say about bundles and signs. Okay, so this is the following issue. So what I showed that in fact I can, if I have a C, let's look at representations of T star, T of T. So we can, I'll denote them by, say, Cm, like this. So this is a one-dimensional representation. So it means that I just take C, and so this is the following representation. It's this action when I take T acted upon on some vector will just go to t to the m times that vector. So these are the one-dimensional representations parameterized by the integers, right? So one question is, so the idea is the following, then using this representation, so this representation Cm gives rise to a line bundle on say XL. And so let's calculate this line bundle for the case of the point. So the idea is this: we just look at X and multiply by, so in this case, X is just a point, so I'll just look at this setup, Cm, is just on the point. And this is an equivariant map. It's a T-equivariant map. And according to this T-equivariant map, I'll have a bundle map on the corresponding XLs. So I have sort of point LT, which is just, as I said, PL minus 1. And here, I'll have the corresponding space for Cm. And that space is, of course, C M, if you like, multiply by CL minus the origin, and then divided by T. Okay, so now what does this mean? So this means the following. We'll look at pairs. So let's just write this down explicitly. Maybe it fits here. So look, let's write down this quotient explicitly. So what that means is that I take a number, so let's denote that by z, and a vector, let's denote that by v, and then I divide by t, so this will be equivalent. So t will be equivalent to tz, t to the mz, and t to the t and t v, because that was the action that we're looking at. Okay, so from here, it's easy to see then if I want to identify what the bundle Cm, the corresponding bundle on PL minus 1 is. So this is now a line bundle over PL minus 1, right? Because this is something that has a one-dimensional fiber with a point. And you come here, you have a map from here to PL minus 1, which is just take this vector here and just take the corresponding point in PL minus 1. The fiber is a Cm, and I'd like to identify what that is. Well, if you want to do that, well, a good choice is let's look at the example m equals minus 1, right? So then we see that, and as this is this tautological subbundle S corresponding to, right, so which is in our sequence CLQ in our usual tautological sequence. So m minus 1 corresponds to S. So why is that? It's because, so remember S now, if we're really honest, was just this subset of a line and V such that V is in the line. And so we just need a map into, this was the tautological, remember, subbundle. And now we just need a map from this thing into this, identify it. Okay, and so there's an obvious map. You take Z, V mapped to Z times V. Okay. If you do that, then, sorry, not quite. So what I mean is V like this, Z times V, like that. Take this pair. So this is non-element of S. And this is an element of this. And the point is that this is equivariant, obviously, because Z times T inverse TV will go to the same thing let's say pi of this is the same as pi of ZV. Right? So, because you take the product here, and this product cancels the inverse in T. Okay, so this is just the... So what we see is that actually, and then of course by obvious multiplicativity, you will associate to the other m's. So this is the general correspondence, is that, so the general correspondence is that Cm thus corresponds to the bundle S minus m over PL minus 1. Right? So this is our final thing. So the confusing thing is the following, that actually you will see very often in products that people write the symbol T not like this, like I did here, but they will put it here. Okay? So that's very common, especially with these associated bundles. But in this case, I decided I'll leave this like this. So this is the convention we use. But, so this is a remark that you will see this definition that where I just have some, I say x, y, and then you put, say, the t here now. And you define this, the following, as the set of pairs x, y, and the equivalence is then that t acting on x, t, say, inverse acting on y is equal to xy. Equivalent. So the equivalence, you know, the action of torus, you twist it on the one of them is, so this is the important thing here. You put, instead of tt, like I did it here, the action was acting by taking t. On one of them, you put an inverse. And that would change our sign convention. Then, if I did that here, for example, then C plus m would correspond to S. Okay? So here, and now it's really confusing what I did because there is an inverse here, but that inverse here is because I choose m equals minus 1. But I still use the t action that we agreed we do. Here, now, I really do the opposite one. So this is now even confused even more. Maybe. I don't know if it's clear now what I did. And the reason you do that here, because now you put t here, and now you think of t as acting on the right, on one of them, on the left, on the other one, and that involves, and that's necessary. For non-commutative groups, that's necessary that you change the sign. So now, anyway, you'll see that, and even today you'll see that this actually happens and is important. So this is a different sign convention. A different sign convention, okay? By convention, I mean that then m equals plus 1 would correspond to s, and not m equals minus 1 if you choose this thing. Okay. So this is one, just I wanted to clarify this thing. And then, okay. So maybe just one more remark here is that, as you already saw it there, is that this thing, as I mentioned last time, so you also did the exercises, so I guess Simone explained to this PL minus PL and the tangent bundle and all those things. Which exercise? I think that was the last one, yeah. Okay, so you saw this today. So the point is, in general, if you look at this, again, by the same logic, I just define now with our usual psi convention t. By this, I can, of course, just forget about x and look at the orbit of this, and so this is necessarily will map onto the quotient PL minus 1, and as I explained last time, it's easy to see that then you get a fiber bundle because you already got rid of this action, so this fiber bundle will have fiber x. And the example we saw that you saw in that last exercise was the following. For example, if x was P1, then what this says is that you'll get a fiber bundle which is easy to identify to be S direct sum S star, which is of course a P1 bundle over PL minus 1. So this is our basic example. maybe already it's just because I'll use this example a lot, and so that's good that you saw it, is that now we can also see the equivariant, so how the equivariant, say, just mappings happen here. So remember, the idea was that if you take x, y, just two varieties, which are now both of them are acted upon by t, and the t action is preserved, then you can always define this xtl. So this induces. Here, of course, when you have p1, so here we act upon the usual way, right? So this is induced by the action x, y, t is tx, t inverse y. Sorry. So that's the action. I take that you had in the exercise. So in this situation, you actually have 2 points, 2 fixed points. So now xt is the north pole, which is 1, 0, and the south pole, which is 0, 1. And these two things already give us examples of embeddings. So for example, the North Pole, right, as a point is a fixed point, so it gives us an equivariant embedding into just P1 with that action, right? And similarly the South Pole, of course. And so to that, there's something like this should correspond. So you should see an embedding of PL minus 1 here into this thing, and you do see it. It's exactly one of them is this corresponds to this S section. So you have 2 embeddings, sort of IN and IS of PL minus 1 into this bundle P S plus S dual, corresponding to over PL minus 1. So 1 corresponding to, so over every fiber you have 2 fixed vectors in the vectors with S and S star, which give the northward and the south pole. It's a bit unfortunate that I denoted this by S, so this is south. Okay, so what else do I need to say? Okay, so now our purpose, so I go back to what we were trying to do. You remember, so I said we defined, so I ended, I think, with this remark, is that in this situation, when you have a map like this, F, then this gives rise to maps F lower star and F upper star, right? And so this is, our purpose now is to calculate these maps. So the point is, let's just do this example. Question, so our plan now, calculate F lower star, the case F equals this IN and I south. Oops. Okay, so let's do it. So first, just to be very, very clear and very explicit, I'm going to write down all the 2 rings first that we have, right? So we have 2 rings, so we've calculated them, so I just recall this. So we need to have maps. So it's the following thing. We have a T of xt. So let me just use x is P1, but it will be shorter if I do it that way, okay? So from here on, just in this example, it's P1. So I have this, and then I have, of course, just a T of x. I have these two rings, and I would like to have now, I have a map, I have 2 maps actually. I have, or I can just look, but I can just look at them separate if you like, xt as a space. Maybe I'll just look at it that way. And then this is just the embedding. Let me maybe, I'll denote it by ridiculous notation M, because iotas on the blackboard are usually too confusing. Okay, so M is the embedding. So sorry, no, I mean it's M star, and then there is a map M upper star here, and so M is this map, is these iotas basically. So M is just the map from xt, which is equal to just north and the south pole into P1. Okay? So I want to calculate these two maps now. The one going to the right and going to the left. So to do that, just to be sure, let's write down explicitly, recall what they are, what these two objects are, and then the map. So AT xt is just 2 points. So you'll just get twice this, you remember polynomial ring, the two copies, if you like. You see these two sections here, the S and S star, they give you two L minus 1s, and they are, of course, sections of these bundles are isomorphic to PL minus 1, and so it's just going to be two copies of that. So it's just the sum of two rings, Z. So I take a copy, so I say zeta north, and this south, why does south and subbundles start with the same letter? You see, that's the thing. So zeta south, okay? And then sometimes I'll put here an O so that you know what it is. Right? So actually we can just remind you what this means. It's a sum of two rings. So it means that, you multiply things separately. So when I say zeta n, just zeta n, that just means that the other coordinate is 0, right? So for that reason, you can write it. This is the same thing as saying that zeta n, zeta s, divided by the relation that zeta n times zeta s is 0. That's the sum of two rings. Because one of them is, if now I'm thinking of zeta n, that the thing 1, 0, and of course zeta n 0, and then multiply with 0 zeta n, then you get 0. So that's why. Am I saying this correctly? No. Well, that's almost right. I made a mistake, sorry. This is almost correct, except that they have two ones, which you don't see here. So there's a 1 here and there's a 1 here, and so there's only one here. So it's almost correct there. So sorry, this is not quite right. So yes, you have a map like this. Anyway, it's just useful to think of that. We can just go back and just use this. Okay? And yeah, so there's a 1 north and a 1 south here, which you don't see here because you only have the 1 here. Okay, so that was this thing. And I remind you, the other thing was ATX, which was just Z, zeta, and eta divided by the relation that zeta squared is equal to eta squared. This was the other thing. So we have these two rings. And I just remind you, so there's two things we need to remember. So first, what is zeta, and then what, what is eta, I mean. What is zeta and what is eta in a sense. So one important thing is that because we have this map always, so this is true for any x variety x, you see that we always have that ax for any is a module over this at of a point. So at of a point which is just z zeta, right? So when we look at equivariant child groups, the elements should actually not simply be rings as a usual child group, but they should be also modules of this. So what this simply means is that they should be defined a multiplication by zeta on them, right? Because if you have a map like this, then you can take the generator of the child group here, you can pull it back and multiply by it, and that's an action, that's an operation that's well defined. So I need to understand what that is. And it's almost evident, you will actually see it even today, that so you need to define those two actions. So I want to define, so need an action of zeta on these two objects. Okay, and so the action of zeta here, so on a t xt, it's just multiplication by zeta multiplication by, so you multiply by a pair, by zeta n and zeta s. And on this, atx is just multiplication by zeta, by the same zeta. That's why I denoted it that way. Okay, so we have these two. Okay. And so one last thing I wanted to remind you is that, well, here actually, because you have eta squared, by these relations, eta is only defined by up to sign, so I can define it either way. So let's say, I don't remember what's better now, let's say that eta is just the equivariant Chern class of say, the tautological bundle, say S, or O minus 1. Okay, so we define it that way. And then we verified last time that this satisfies this relation. Okay, actually we'll do this again. Okay, so now I have completely described the ring and I understand everything completely, so I can now calculate the maps. So let's do that. So in fact, of course, this map is easier, the pullback. And this is because, so for example, it's from the naturality of Chern classes. If I take M upper star of, for example, so now I take an element in this ring, and this ring is this ring, so I can take zeta or eta. These are the two things, so let's take eta. Of course, so this is just going to be, so by the natural, so this is just going to be, let's just substitute M star of C1T of S. So this is the tautological bundle on P1, and I pull it back onto these 2 points. So then you see, what do I get? So this is just, because it's Chern classes are natural, I can just take this first equivariant Chern class of the pullback of this bundle of M upper star of S. By this I mean that I take the bundle S on P1, so this is P1, North Pole, South Pole, and there is this bundle on this S South Pole, and then there is this bundle S on it, which is a tautological bundle. And I'm saying, let's take the first Chern class of this bundle S and pull it back to these 2 points. That's, of course, that's by naturality of Chern classes. The same thing is if I pull back the bundle to these 2 points, and then I take the equivariant Chern class. Okay, so let's do that. And of course, then what that is just equal to C1T of, so it's just S restricted to the North Pole, and there, you remember the weights I defined them, the weights was 1. So I have to take S, well, maybe I'll write it down. So it's S restricted well, now if I write n, it's going to be even more incomprehensible, but anyway, maybe it's not so incomprehensible. The North Pole, and then S restricted to the South Pole. Right? So, but now these are just 2 points. And you just have to know the weights. And the weights follow from the way I define the action. One is T, and the other is T inverse. So this is just C1 T of C plus 1, and then C minus 1. That's what it is. And so this corresponds here to the North Pole, and this to the South Pole. Okay. And so then, by the calculation that I did at the beginning, if you have Ci, that corresponds to minus zeta, actually. So this is just minus the pair minus zeta n and zeta s as an element. So this is now an element of this ring here. Okay. So that's because of this change. Remember, Cm corresponds to S. Yeah. Is this convincing? So now I stop for a second. No? It's incomprehensible?
Aren't the weights 2 and minus 2? Or
No. You'll see. That comes now. No. This is just simply you restrict. You see, you have, and you restrict the bundle, you just have a, a complex vector space with a certain weight. That's what you get. It's not clear? So again, this is how we defined eta when we were calculating, and then we did this tautological sequence, so that's how that came about. And now I just pull it back to a point, I get a vector space with a certain weight, and that's the weight. So is this clear?
What would happen if you restrict it to any other point?
You can't. So that's what we were discussing last time, that it's only defined this whole thing in the category of equivariant maps. And there are actually only 2 equivariant maps that you can. There's not so many equivariant maps now you have, because there's only invariant subvarieties are these ones. So it's not defined. A point mapping here is not defined in our category, because cannot be made equivariant. Yeah. Okay, so this was the easy part. So now comes the hard part. So we would like to calculate what this push forward is. Okay. So maybe I'll also do the other part. But the other part is easy, so that's we sort of verified last time. But again, that if you now just take, well, you can just see it the same way. You can take the other generators, so if you like, zeta corresponds to just C1 of the trivial line bundle. So just O, so I don't know how to do the trivial line bundle. Trivial line bundle over P1, but with the, so how to say this? Now maybe not, I'll write it maybe more formally. It's like this, so it's C1 of T, which is that you just take C P1 and you take the trivial line bundle, so you just multiply by C1. And it's the first rank class of this line bundle with weight 1. That's the other thing. And then you can see that also that then AM of zeta. So then, of course, you just restrict on both of them. Then obviously you just get plus 1 is C1 and C1 of both fibers. So then this is just this thing, theta N and theta S. With a little dot that's an O saying that's south. Okay? All right. So now the hard part, or the interesting part, well, they're both interesting. Now what maybe here already make a remark is that this map is rather exciting. So, so one can verify, one can see that this map M star is injective. Injective. And this is sort of one of the key points. So what this means, well, let's just look in degree 2. Check in degree 2. What happens in degree 2, or degree 1 maybe, or 1? Well, 1, sorry. In the child group, it's degree 1. So what happens in degree 1? So here I have Z, well, in degree 1, so A 1T of P1 is just equal to Z eta direct sum Z zeta, right? Because it's this thing. And so the relation is a quadratic thing. And A1T xt, so T is just Z zeta north plus Z zeta south. Right? And the map is a matrix that you just see here now. The map is just M star is just given by this matrix. So 1, 1 and minus 1, 1, if you like. So you have two lattices, Z squared, that's the second child group. And the map between them is this matrix, right? So zeta goes to 1, 1, and eta goes to minus 1, 1. And this matrix, this matrix has not, the determinant is 2. So in fact, this is an injective map of one lattice into the other lattice. Is this thing, right? That you have 1, 1 and minus 1, 1, and here this is not in the image. So so this is the image. So this is zeta n, zeta s, and this is the image of so this is M star of zeta, and this is M star of eta. And this thing is not in there, actually. See, so this is just... But why this is interesting is because now, so this is very strange if you think about it. That it's, if you could do the same thing non-equivariantly, as you said, I mean, of course, if I just take a point, then if I take a non-equivariant category, then I can just, every point, you can just embed any point, like this point or this point. Of course, they all give you the same. And you don't, of course, you totally lose information. You don't see anything. When you pull back the child groups from the P1 to point, you just lose every information. And here, not only you don't lose information, it's an injective map. So that means that if you know the image of the child group to the restriction of points, you don't lose any information. It's the opposite. Your problems actually have to identify the image. But by, yeah. And so this is actually the main point of localization. So one can think of so the point is via, maybe I write it here, that via M star one can use a txt to describe atx. And this is really not the same thing as what happens if you just use usual child groups, where this is absolutely not true. Okay, so now let's let's try to describe the other map. So the other map is M star, and this is what we discussed last time. So, but this is more or less was your exercise, I think, right? So what you do, you can look at so you can look at this point, say. So 1, for example, you can look at the point 1 north. So remember now that that's one of the elements of the ring. So 1 north is an element of maybe right. So by 1 north, I mean 1 north, and then 0 south. That's what I mean by this. For example, you can look at these elements. So it just means the embedding of the class of the North Pole into here. And so as we discussed, this is just the usual, I showed you this last time. So when you have a map yx, then you have f, then f lower, f upper star, f lower star of y was just so this is codimension D, so it's an embedding of a variety of codimension capital D, for example. Then this was just the top, so Dth Chern class of the normal bundle of y in X. This is the general pullback formula. And so this one, parenthetic remark, then this one, if you use this formally, then you see that this is just going to be a 2, so I actually, to follow this, then I'll do this as well. So this, we calculated this, and this was also your homework problem. So this is 2 zeta n. Just a second, so now I have to be careful. So it's hom n 2, so it should be minus, I guess, right? It's minus 2 zeta n, and this will be plus 2 zeta s. Okay. And so this was more or less your homework, and you can just calculate this by looking on this corresponding model, you remember. So you explained this somehow, more or less, or? Yeah? Okay. So then, okay. So actually, if we look at this, then this is kind of amusing, because now I can put this on this diagram. So maybe it's slightly better I will expand this diagram now just in this way, so that so what is happening here, as we agreed, that this, in our example at least, in degree 2, this is an embedding here, right, using this matrix. And now if we look at the image of these, then what we see is that this, on the other hand, I do a bigger picture now. So I'll just take one more minute. So the idea is that so this is what we see here is just the second equivariant Chow group of the fixed points, so x t, so this is just z zeta n direct sum z zeta s. Okay. And so here is, of course, zeta n then, and this is zeta s. And then we saw that this is the m upper star of zeta coming from x, the equivalent cohomology of x, and this was the m upper star of eta. And then here what we see is that this is the, and so this thing is sort of missing here. And then here we see E, so here, I need maybe a different color now, it would be better. So maybe I already here use a different color. So it's this lattice, and then there is another lattice, it's this one. So the one, this, and this, and this. So the blue one is the m lower star of, if you like, z 1n direct sum z1s. And this is the lattice where you have, and is just equal to z twice z to the zn plus z zeta s. So with the double, right? Because there's a 2 here. And so, yeah. And then the other one, as I explained here. So finally, we have the following thing, that if you take A0 t of xt, then this actually embeds, because you see, this green lattice contains the blue lattice. Right? If you take twice the lattice that contains the elements that are generated by 1 minus and 1, 1. So this actually embeds this m lower star to A2 of, or A1, sorry, of x, x. And this, in turn, embeds into A1 of xt. So this is the picture we have. And this is a rather very general situation. And so this we are almost there, you will see. I mean, this is, so the one thing it should amaze you is the fact that this is already embedding. So something that was very complicated, Chow groups, now we look at something even more complicated, equivariant Chow groups, and all of a sudden, this is just embedded in some completely obvious ring, which is just direct sums of Chow groups of fixed points. And this is true also in complete generality. So we'll be able to understand what's happening here just by some direct sums of polynomial rings. And the other thing is that we also have a description, and so you see what is happening here is the following, just so that, well, actually, one can easily describe what this map is directly with this eta business. I will do that too, maybe. I'll do that at the end. So, but actually, I didn't tell you what the image here is with these zetas and etas. I immediately went here and explained this combination, what that means. Okay? We'll actually do that, but what the important thing is that in these coordinates, I'll call these even coordinates. You can call, if you have a class here, you look at the image and it has coordinates. In these coordinates, I actually have a complete description of the push forward as well. So if I think of this m upper star as just coordinates on here, then this map here describes the push forward map, which is the most important in a sense in intersection theory, in these coordinates. Okay, and the push forward map is just multiplication by this thing. Okay, so I continue from here. Okay, so let me continue. This is going to be very exciting, except I made a mistake again. So, of course, yeah, I got myself confused with these, with the signs. Because, so remember, when you have weight 1, that goes to minus, right, because of this sign convention. I mean, minus 1 goes to plus. And when you look at the tangent weights, at the end, that's HOM SQ, So the tangent, remember, T of P1 is just hom SQ, so that's S dual times Q. And so for the North Pole, this would be the S had weight +1, so this has -1 and -1, so it's weight -2, and that's why I wrote here -2. But that's of course incorrect because we agreed that, that you have to have a minus sign, like there. If you had the weight +1, that gave me a -1 here, so when you have -2, so that should give you a +1, so I'm sorry. So it's the opposite. Okay. All right, so modulo that, everything is fine. And so now we go to our sort of final calculation. So first, let's just step back a second and calculate this thing a bit more now, this diagram a bit more honestly. That's not difficult because we have coordinates. So there's two remarks. So let me just calculate now this one a bit more carefully. So calculate precisely this m lower star. So there's two things. One is that we have permanence. It's called permanence. So you remember that just says that f lower star times f upper star alpha times beta is equal to f lower star of beta times alpha. So if you push forward, you multiply something by a pullback, then you might as well just not do that. Just push forward and then multiply by whatever you had. So this, of course, applies here as well. So this allows us to calculate this thing in general. So this means that if I have, for example, m lower star times m lower star times star of some. So what we calculated was this. One, say, well, I'll just write it in general right away. So if you had some gamma and delta here, then it will just mean that it's the same thing as if you had the 1, but now you just have to multiply by, if you had a gamma times 1, we'll go to gamma times this thing. So which is going to be maybe just so that you understand what I'm talking about. So these are two polynomials now, gamma of zeta n, and then delta of zeta s. And so then it's just going to be gamma, and you multiply by 2 zeta n, and then delta times minus 2 zeta s. So this is minor point, but so this is not a complete description of that map. We're mainly interested in the first child group, though. Okay, and the second is sort of an obvious remark, which you could already notice before, is that if you look at this thing, so you multiply by 2 psi n or minus 2 psi n. So, of course, 2 psi n minus 2 psi n is minus. So just remember that m. What I'm trying to say, that, yes, maybe this way, that if I want to find m upper star of something, which is this vector, this minus 2 psi n, 2 psi s, then this is, of course, minus 2 eta. right? Because eta was, no? Oh, sorry. Again, I'm minus, right? Huh? Yeah, there's a minus. Which minus? No, I think this is not right. Because eta was minus psi n plus psi s, and now, because I changed the sign, I made a mistake, and now if you, yeah. No, this is correct, right? Because eta, you remember, was minus psi n plus psi s, and so it's minus 2 eta. Okay, and so now I can also describe this map, if you like. So it's just, yeah, so I mean, the image of 1, 1 is simply minus 2 eta, right? So m lower star, for example. M lower star of 1, 1 is just minus 2 eta. Yeah. And then, of course, otherwise, you use permanence to define the corresponding equations. Okay. So that's one thing, and so am I ready to do this final thing? Yeah, so now the final idea, so the main point here. So again, so this came from the fact that I know, I mean that this thing is an embedding. See, if I know the combination of this thing, then I also know where I was, and that's what it is, right? And so now, finally, I do one more map. So the usual map is that I just map this to a t, so of a point. Okay, so this is just. So this is the final integration. Okay, so I use, and we are going to be discussing this final pi. So pi is simply, of course, this is always an equivariant map, and this is what we're doing. Okay. So in particular, I mean, when we usually calculate things, what we are interested in, I remember, is things like we are interested in Chern numbers. So in general, what I'm talking about is you have, say, some bundle X. So this is some vector bundle, and suppose dimension. Now for a second I go from x equals p1 to the general case, but then I'll come back. So dimension x is equal to n. Then I can, for example, so we are interested in Chern numbers, yes. So I'm explaining what Chern numbers are. So you have some now, let I1, Im to be some numbers n. So I look at some integers whose sum is exactly the dimension of n, and then I can form an element of the Chow group, which is of top degree, or degree 0, codimension 0. So then I can just look at C1, Ci1 of E, well, just the, I want to write the product, etc. Cim of E. This will be now in n of x. and then we just integrate the integral of this polynomial is the corresponding Chern number. Sorry. Okay, so this was it's a general problem that we are interested in because so just if you remember, one example we had is that the number of, so that was our very, very first enumerative problem. The number of lines which intersecting 4 given lines in, say, 3 space was equal to, you remember that was a Chern number, that was just the integral of C1 of the tautological bundle to the power 4th over the Grassmannian of 2 planes in 4-dimensional space. Right? So remember this is what we did at the very beginning. That's why we introduced bundles and Chern classes, so that we could, a lot of enumerative problems could actually just by calculating things. So this is what we're aiming at. And I'm going to show you how using this sequence we can actually do that. And we are basically there. And the reason, so of course, so at the beginning, for a second, this was a non-equivariant situation. Let's just first look at this equivariant map. Let's try to understand what that is. And we basically have it. So let me show you why. So I straightened this sequence here. We should think of it this way now, because the logic is the following, is that we use this map, as is an embedding, as coordinates here. And we try to understand this map. Of course, this map is what's very difficult in principle. So, but there is a very easy map now. And the very easy map is the following. It's going from here to here to here, right? And remember that, so pi is this map, this is the push forward. And of course, push forward is associative. So the point is that, now first I'm just doing in the equivariant setting. So in our equivariant setting, we need to understand Chern numbers. So calculating Chern numbers is, well, equivariant Chern, maybe equivariant Chern numbers is the same as calculating this map, more or less. This map pi lower star, understanding it. And now we have a relatively good way of understanding it, because on this thing we have these coordinates. So we can think of an element here and then try to understand its image by describing it here. So that's the easy part. But now we have an amazing tool, which is that we can, so pi star is hard, but the combination of m star pi star is easy. Okay, so why is that? What is m star pi star? Well, that is just m star pi star is just simply the map it just maps xt to a point. So this is just a finite set of points being mapped to a single point. That's all, right? So in P1, we can go back to think about P1, is just you're just taking 2 points, mapping to 1 point. So this is very easy. This is quite clear that in this case, so now we are back to just, this is to illustrate this P1. This works in complete generality. So now back to P1. Of course, it's easy to see that. So remember now, pi star m star of, and so now I just need the sum of these two rings. Say P, so now I have gamma of zeta n, so this is one polynomial and some delta, sorry, not enough space. So I take pi star m star, and then I take an element here, and that's just two polynomials, gamma of zeta n and delta of zeta s south, and this is just the sum of, so I just need to give you a single polynomial, the equivariant child group of the point, so it's just going to be the sum gamma of zeta plus delta of zeta, right? Because it's just the 2 points, and each of the points separately gives you a copy of this. So this is easy. And so now we have an amazing opportunity, because now we can, for example, if something is in the image of this thing, so if I take an element that's in the image here, then I can simply, instead of integrating this, which is really the whole purpose of enumerative geometry, I can just pass by here and come here, go here and here. Okay, and so let's see, we already have an example here. For example, we know that if I take pi star m star of, say, well, let's say 1, 1, so now I just mean this is one north, one south, so these are two polynomials. One is in xn. Okay, so this is equal to what? Well, according to this, just take the 2 points, this is 1 and 1, so it's just 2. 1 plus 1, okay? So this is clear. But now we know what m star of 1 and 1s is. Remember m star, and this is the key, m lower star of 1, 1 was minus 2 eta. So this tells me that I know that pi lower star of minus 2 eta is 2. So that means that the integral that pi lower star of eta is minus 1. So I learned how to calculate the Chern, and remember, eta was the tautological number. Sorry, the eta was the C1 of the tautological line bundle over these, O of minus 1, and so its push forward is, its Chern class is supposed to have integral minus 1. You see this minus 1 here. So is this some kind of miracle? So we calculate some integral, some intersection number without intersecting, just somehow by this sort of amazing sequence. It's still somehow, well, you'll see in a second. It's completely incredible that this actually works. So, yeah. So, yeah. So just need one little remark. So equivariant versus non-equivariant. There's a small technical detail here that here, when I was telling you that I'm interested in calculating Chern numbers, so I took the Chern polynomial. So, yeah, maybe I'll write it in this form now. So maybe just add here this thing that, so what we calculate is that the integral of, so I mean the push forward, that's the same thing, right? So the integral is the push forward to the point of C. Yeah, when I write integral, I just mean the push forward to the point in the Chow group. So C1 T of S is equal to -1. This is what we proved, right? It's just, it's the final. So the only thing is that here you have an equivariant Chern class, and here I wanted a non-equivariant Chern class, but it's a simple exercise that these things are the same when the dimension is correct. So this is an exercise is to see that in this situation, so going back to that thing in general, suppose now I have an equivariant situation, then the integral of the product of so again C1 CI1 E etc. CIM E. So this Chern number that we want to calculate is just a number. Now let's look at the equivariant case. If you calculate the dimensions, you will see that just like here, because you lose exactly that many dimensions when you integrate, so this was a rank 1 bundle on a one-dimensional space, you lose as many dimensions, so you end up in constant. So this is always going to be a number if here sum of IM equals to the dimension of X. So integrate over X. Ij. So if you take the sum, so this it will be a number. So it's not very surprising that this number is the same as if you just did it without the equivariant thing. I mean, it's also a number. That number is the same number, and that's just there's a simple geometric reasoning for that, but I'll skip that today. CIME. So in this case, but this is important that you need to have this. Of course, if you go higher, if you take an equivariant Chern number where the sum of the indices is more than the dimension of the space, then of course this will not be true. I mean, then you will get some other homology guys. But if they're precisely the sum of the indices is the same as the dimension of X, then there is no difference between equivariant Chern numbers and usual Chern numbers. You'll do some exercise, you'll see this is some simple fact. But in any case, using this miracle, we calculated the equivariant Chern class of this. So this is the tautological bundle has Chern class -1. We calculated this using this technology. So without any transfer, so there's no transversality. We're intersecting things without any. I don't have a watch. Sorry. Let me write down the general theorem now. So there is a certain device that's useful here. Just this. So-called Bott residue theorem. And so it's the following thing. So this is the setup: X, smooth, projective, dimension n, and you say I take this bundle E, vector bundle, and everything is equivariant. So this is an equivariant vector bundle, just like that, and with an equivariant action. So we assume that XT, this is not necessary, we'll look at the more general case as well, but for now, XT, the fixed point set, is finite. Okay. And so I need one more device. So here it's not quite visible, but what we were doing is I kind of got lucky, right, in a sense. You could say that I just took this 1, 1, and I got -2, 8, and then I divided by -2. So in general, of course, there's an actual easy device to, I erased now my sequence, which I want to have. So I'll put it up here, maybe just, it's the same sequence. So this is these 4 things you should have in mind. Okay. So you see, yes, so our purpose is that I want to calculate this map by going by here. So of course, we saw when I calculated the image that the complete image here is not the same thing as this. And it's obvious cannot be because, for example, if I take something of degree 0 here, it will go up to top degree here. Right? So remember that m lower star increases degree by as much. It was multiplication by the tangent class. So that it seems like I got lucky here, but I can do something really crazy, which is I can just divide, introduce a division, which will then make this thing an injection. And that's the next, and that's a little technical device. So what the way to do that is that I will tensor everything with this division. So to make this work, we tensor our rings with Laurent polynomials in zeta. Okay? And so this is this place where you need the other convention. So if you have, suppose, so this is a general construction, if A is as a zeta module, so which all of our rings are, because all equivariant rings are, then you can simply define just I forgot, what is the notation? Yes. So you can simply define so now I will need to put, so let's just put a zeta here, which is not going to be so great in general, but this notation is just defined as just A, and then you tensor with the, so these are the Laurent polynomials, so you have zeta and zeta inverse, and then, of course, these are now both Z zeta modules. So I tensor them in this way, and I'm putting this in the middle and not on the right. And so this is important. So what I mean by this is that if I put the Z zeta here, this needs to preserve degree. That's why I have to do this. And so so you say that A zeta, or if you like, so these are modules, so I can multiply by zeta, so zeta A B should be equivalent to A zeta B. And this is the, right, because it has to be homogeneous. I cannot do like what I did. I cannot say AB is zeta A zeta B because that would not preserve the degree. So now I'm doing this other convention than I did with the signs. But this is, in this setup, it will be very natural. You won't even notice it that I'm doing this, but I'm just saying. Okay? And then the first theorem upon tensoring this way, this becomes an isomorphism. Upon localizing this way, it's called localizing. Yeah, this is a term, I'm not even going to say it. Yeah, doing this. Doing this, I won't use localizing, you'll get even more confused, to our groups, our sequence. So this sequence, the one, these 3 elements here, the maps become isomorphism. So this is actually a theorem. Okay? So if I'm allowed to divide, you see, then I can even produce 1, for example. Okay? So how am I going, for example, how I'm going to produce 1? Okay, so let's just try, e.g., an example. Say in my case, as I said, because the map is simply, so let's just look at this map, right? We know that m gamma delta is just equal to no, I forgot what that was. That was the sign where I had plus, right, or something. 2 psi n yeah, how to say this? Now let me just do the complete sequence. Maybe it's better. So m upper star gamma delta is just, yeah, that's better. Sup psi n gamma minus 2 psi, zeta, sorry, s delta, right? So that was our formula. So obviously this cannot be an isomorphism, right? Because it increases degree, and these are 2 polynomials. If I put 1, 1, I will never get 1, 1, for example. So how can I get 1, 1? It cannot be an isomorphism. But if I arrive to divide, of course, by zetas, of course, I will be able to get 1, 1. So yeah, so gamma divided by zeta, so if you like, sorry. It's just going to be the same thing, but now I can get rid of the zetas because zeta, remember, goes to zeta and zeta s here. So this will be just 2 gamma and minus 2 delta. And now it's easy to get 1, 1. Okay, so when I divide by, if I'm allowed to do this division, okay, I added these inverses, then I can easily produce any element now. And so this way, we can now easily produce any element in the image of EM lower star and thus calculate the integral. So let me just check the time. 5 times. So let me just write down the theorem. So the point is that if I take, so maybe just first the proposition. So now this is in the same general setup, that if I take, suppose now I have some sigma, which is in the equivariant cohomology of X. And now what I'm going to do, I will calculate, I take sigma and I multiply it, I divide it, opposite, by the equivariant Chern class. And so I take the dimension of X is n, I don't know. So the top equivariant Chern class of the tangent bundle of X pulled back. So maybe I'll need a little more time to explain this better next time. Okay, so if I divide this, and now if I push this forward, then I will just get back sigma. So maybe. So this is sort of the general form that we need to understand. So the idea is I take some element sigma, and I want to produce it as an image of something. And the thing you have to do, well, you pull back sigma so that you can identify it in these coordinates. And then you have to divide it by what you would be multiplying when you push forward. And this is what you would be multiplying by. So you divide that and you push forward, and this factor disappears, and you just get sigma back. So this is sort of the fundamental formula. And so if you just give me a minute, I wanted to show you some application, the application of this. So then finally the Bott residue formula, so the formula itself, formula says the following, is that the integral of these Chern numbers CI1 CI1e CIME in this setup that I set up here, x is just equal to, and then I just integrate this element now in sort of the obvious way, which is just the summation. Remember, the push forward on xt was just the summation. So it's the sum of the contributions of each at each of the fixed points p xt, and then you just look at the corresponding product. So C1 T CI1, sorry. So it's a little, in this general, it's a little complicated, but EP, and then you just multiply it. So these are now just vector spaces. So this is the fiber of E at P, and you take the corresponding Chern number. This is IM, T, and you divide it by that thing that you need there, so by CNT of EM star TP. Or just, you don't need the EM star, just TPX. This is the pullback is TPX. Okay, so this is sort of the final formula. And, sorry, I'm the other way around. I1, T, no, what am I doing? No, this was the other way around, sorry. You put it up, sorry. One of them was the other end. I1, T, this was CIM, T, and it should be CNT. So just, I know I ran out of time. So just give me 1 minute. I just want to show you this thing because it's really incredible. So, so what this looks like in reality, I want you to, let's just, 2 minutes, sorry. So let's calculate this integral C1 to the fourth of S on the Grassmann of 2,4 using this formula. So since I have to do it quickly, I'll just do the numbers, then you will have to work it out. That was one of the exercises. But so what does it look like? So now just C1 times C1, etc. So the idea is that you have this action now on C4. So sorry, this is a bit over time. TA, TD, right? So 4 numbers, 4 weights on C4. So A, B, C, D are the usual thing. These are different integers. Okay? Now these different integers, well, I'll choose different integers. So let's maybe -2, -1, 0, oh sorry, let's not do 0, 1 and 2, say. These are 4 different integers. Okay? This is the action. So then what does this formula say? We'll have the fixed points, so you know this, you've already done this. We act by this thing, so there is 6 fixed points, depending. So C1 S to the power 4 on the Grassmannian will be the sum of 6 terms. Okay? And this sum of 6 terms, so you look, C1 is actually the sum. It's a rank 2 bundles. It's the sum of the two. So I'll just do one term here, so that will look like this. So if you choose the first term, it will be a sum. So the first term will be like this. You choose the first fixed point, which corresponds to A and B. You take A plus B, and you raise it to the 4th power. Okay? That's because you have C1 to the 4th. And then you divide by the weights of the tangent bundle, which are the differences of this number. I mean, this I'm not going to explain now because I don't have time. But it's just going to be something like C minus A, D minus A, and C minus B, and D minus B. That's one term, and then you have plus 5 terms, depending, you choose another pair of numbers, so altogether 6, like you have AD, and then you do all those numbers. Okay, well, there we go. So you get this, and you choose these numbers, and then these are the 4 numbers, and you substitute them. So let's do it. So it's 6 terms. It takes a little while, since I don't have time, so I'll just tell you what happens. Well, here you can see that A plus B, if you have, say, minus 1 plus 1, that's going to be 0, and this is also. So 2 terms are completely 0, and then 2 other terms are the same. If you choose them, this one or this one is the same. So actually, there's only 2 different terms. So there's one when you choose the case when you have 2, 1 up there. So two essentially different terms. And they are the same. So one of them is 2 plus 1 to the 4th. And then you take all the corresponding differences, and you calculate it, and you have 2 times 3 times 3 times 4 here, actually. That's what you get. And then you have twice. And then plus, the other case is when you have the across like this, say 2 and minus 1. So you'll have 2 and minus 1 to the 4th. And then and there you have some signs because of these differences. So you will have, if you look at the signs, it should be 2 minus 1. So you have a 1, you have a 4 and a 2, and then 1 and a minus 1. So you have a 1, a minus 1, a 4, and a 2. And you also have this twice. So again, 1, minus 1, 4, and 2. Okay? So if you calculate this, then you just get twice 9/8 minus 1/8 finally. So again, it's 3 to the 4th. You cancel 2 3s, and you get 9/8, right? So you see 3 to the 4th, 3, 3. Cancel. And you get 9/8. That's where the 9/8 comes from. And there is twice. And then you have another thing, the other 2 terms. 2 terms are 0, 2 terms are like this, and 2 terms are like this. And that's 2 minus 1 to the 4th. That's 1 to the 4th. And then it's 1 minus 1, 4, and 2 if you calculate these differences. So that ends up to be just minus 1/8. And 9/8 minus 1/8 is actually 1 times 2 is 2. So you have 2 lines that can intersect 4 lines in 3 space, which is probably one of the most amazing, calculations. I was just thinking this morning that, I think if you go and you show Schubert calculus to Euclid, remember the Schubert calculus is when you have these 4 special, that I showed you, special configurations where the 2 points intersect, and then you can see that the answer is 2. Then, Euclid would say, well, it's nice work, yeah, I kind of knew that, but, yeah, good job. But, if you show this to him, I think his mind would have been blown, I mean, this is just completely incredible. So, yeah, the answer is 2. Okay, well, sorry, I'll clarify some of the points, but I wanted to get here to the end.